Welcome to the VR Linear Algebra project. An interactive environment designed to make linear algebra concepts more accessible and engaging through virtual reality. This project offers interactive hands-on learning experiences that allow users to explore key linear algebra concepts in a virtual space. When entering the virtual space, users are stationed in a lobby environment. A yellow sphere, called the menu screen, will be prompted in front of the user to activate when needed. To move the menu screen, simply grab the yellow bars and sphere of the screen to adjust its orientation. The VR environment includes 6 core modules, located on the menu screen. Each module is focused on a core concept of linear algebra: vector manipulation, linear transformation, vector addition, linear systems in 2D, linear systems in 3D, and Gram-Schmidt module. Vector Manipulation Module. In the VR Vector Manipulation Module, users can interact with vectors in 3D space, form a vector alignment, and generate vector planes. To move a vector, simply pinch its endpoint and drag it to the desired position. To align 2 vectors, bring them close together. When aligned, the system will display the ratio of their magnitudes, providing a visual representation of their relationship. To generate a vector plane based on 2 vectors, begin by pinching the body of a vector to select it. Then, select a second vector. A plane will automatically be created with respect to the 2 selected vectors. To make a third vector linearly dependent on the generated plane, select the third vector. The third vector will automatically snap onto the plane, aligning itself accordingly. To deselect any active vectors, simply pinch them again. To assess the graph interactively, users can drag the axis points to rotate the graph for a better viewpoint of the vectors. This process offers an engaging and visual approach to understanding core mathematical concepts such as vector addition, alignment, and linear dependence. Linear Transformation Module. In the Linear Transformation Module, users can perform linear transformation on a matrix through a variety of operations, including reflection, scaling, shearing, rotating, and projecting. The formula displays a base matrix to be changed, as well as a prime matrix result with respect to the applied matrix of transformation. An image functionality is also included to help visualize the behaviors of the linear transformation. To perform a transformation, select the transformation you would like to apply. For reflect, reflections are shown with respect to the y-axis, x-axis, y equals x symmetry line, and y equals negative x symmetry line. For horizontal and vertical scaling, users can manipulate sliders to apply scaling to the matrix of transformation. For horizontal and vertical shearing, users can manipulate sliders to apply shearing to the matrix of transformation. For rotate, a dial will appear for users to perform a rotation. Angle values are displayed to inform the degree of change. For horizontal and vertical projection, users can project the transformation to project to the horizontal and vertical axis, respectively. Vector Addition Module. The Vector Addition Module allows users to visualize the result of adding 2 or more vectors by generating a plane from the vectors and displaying the combined vector. To generate a plane with respect to 2 vectors, select the 2 vectors you would like to form a plane from. When a plane is generated, the combination of the 2 vectors will be created. To move the combined vector and add-in vector, simply drag the endpoints of the vectors to visualize the relation of the combined vector with the add-in vector. To generate a combined vector of 3 vectors, simply select the third vector. This will form a parallelepiped, encompassing vector addition in the form of a 3D-dimensional space. Users can interact with the vectors by adjusting their positions, observing how the combined vector dynamically updates in response. By exploring these interactions, users can better grasp the principles of vector addition and their applications in both 2D and 3D spaces, bridging the gap between abstract mathematical concepts and tangible spatial reasoning. To deselect the vectors, simply pinch the active vectors you would like to deselect. Linear Systems 2D Module. In the Linear Systems 2D module, users can perform row operations by moving lines on a two-dimensional graph, adjusting their slopes and intercepts. To interact with the linear equations in the graph, simply pinch and drag the lines and the intersecting point. To perform row operations on the graph, users can use the buttons available on the provided screen on your left. The available operations include setting coefficient to 0, setting coefficient to 1, swapping equations, and setting random values. Users can utilize the 3 function operations to perform row reduction on the graph. The lines in the graph will display a visual indicator when a row echelon form has been achieved. The Linear Systems 3D module expands on the concepts from the 2D module to a 3-dimensional space. With a 3D graph, users can interact with planes instead of lines, exploring how systems of 3 equations intersect to form lines, points, or no solutions with parallel planes, and perform row operations with 3 coefficients. To interact with the linear equations in the graph, select an equation as a pivot, then grab the planes to rotate with respect to that pivot. To perform row operations on the graph, you can use the buttons available on the provided screen on your left. The available operations include setting coefficient to 0, setting coefficient to 1, swapping equations, and setting random values. To set a coefficient to 0, select the 0 button, select a coefficient from a row you would like to reduce from, then select a target coefficient from a different row you would like to be reduced to 0. To set a coefficient to 1, select the 1 button, then select a target coefficient of a row to be scaled to 1. To swap the order of equations, select the swap button, then select the 2 equations you would like to swap their rows of. By utilizing the row operations, the system can be solved through row reduction and be converted to row echelon form. Once the system has achieved row echelon form, a visual will be displayed in the graph's planes to indicate a solved system. A set of inconsistent and dependent system orientations have also been added in the module for users to perform row reduction and solve specific selections of problems with unique solutions, allowing a better understanding in the different behaviors of systems of linear equations. Gram-Schmidt module. The Gram-Schmidt module allows users to perform orthogonalization with two vectors. To perform orthogonalization, users can simply press the Orthogonalize button. Once pressed, a message on the menu screen will prompt you to begin the first step by selecting the desired vector to orthogonalize with respect to. Once selected, the menu screen will inform you to begin the step of dragging the desired vector to the orthogonalized area indicated by the provided visual lines. Once the vector has been orthogonalized, the user will then be prompted to proceed to the next step in normalizing the two vectors to complete the orthogonalization process. The orthogonalization is now complete. The project takes advantage of virtual reality's immersive capabilities to provide a more interactive and engaging way to learn linear algebra. Rather than reading or watching static examples of the concepts, users can directly manipulate mathematical objects, reinforcing their understanding through physical interaction. By combining virtual reality with linear algebra education, this project offers a more hands-on approach to learning, making abstract mathematical ideas easier to grasp and more engaging to explore.